Okay guys, today we're looking at trigonometry problems. And our goal is to recognize when to use our different rules. So when to use SOHCAHTOA, when to use sine law, when to use cosine law to solve for sides or angles in these triangles. So we have a lot of different tools at our disposal here. And really it's important to use it's important to know when we use each one of these tools. So we're going to run through each of these, and you can write down when we use each of these tools. And some of them are pretty obvious. So we're going to use the sum of the triangle theorem, so the angle sum of the triangle theorem, when we have two angles in a triangle that we know, and we want to use it to find the third one. And Pythagorean theorem, so we're going to use a squared plus b squared equals c squared. When we've got a right triangle, we know two of the sides, and we're trying to find the third. SOHCAHTOA is something that we've learned this year, and those are our primary trig ratios. And we use that when it's a right triangle and we are trying to find a side or an angle and we know two other pieces of information. And we use sine law when it's not a right triangle, and when we know partners. So if we know the value of an angle, and we know the side across from it, we know that value, and we're trying to find some other piece of information, either an angle or a side, then we can use our sine law ratios. And we use the cosine law in a similar situation when we've got a non-right triangle. Okay? If we do not know partners, then we can use one of the cosine law, or coleslaw, as you might want to call it. We can use the cos law when we don't have partners, and there are two versions. There's one version we use when we know all three sides, and the other version we use when we know two of the sides and the angle in between them. Okay, so there's a lot of different formulas that we use here, and it's important that we know when to use each one. So we're going to go through some examples here and talk about what we use in each of these cases. So in this case, we're being asked to find AD. And AD is the height of triangle ABC. So I'm actually going to call it H. So in triangle ABC, we don't, as it is right now, we know the length of BC is 250, and then we know some of the angles within triangle ABC. And you'll notice that within triangle ABC, we've got two right-angled triangles inside that non-right angle triangle. So let's fill in some information that we can find right away using angle sum triangle theorem. So we know that this angle here is a right angle over on this side of D. We can also find angle B, because we know that angle B is in triangle ABD, that right angle triangle. So angle B is equal to 180 minus this 90-degree angle and minus the 54-degree angle that's at the top. So if I do that subtraction, I know that angle B is equal to 36 degrees. I'm going to move this up here out of the way. But we know that that angle is 36 degrees. We can also find this angle over here. So angle C is equal to 180 minus this 90 here minus the 25 degree angle at the top. So this angle in the corner here is equal to 65 degrees. So all that information we can find by using ASTT. So if I was going to list my reasons here, this is ASTT, and this is ASTT. All right. Now, in order to find this H value, which is that side AD, we really need to find one of the sides in one of these smaller right angle triangles. So either triangle ABD or triangle ABC. I'm going to try and find this side over here, side C, that's opposite angle C in the big triangle ABC. I'm going to find that first to help find this side in the small right angle triangle. So, in triangle ABC, I'm going to use sine law to find side C. Okay, so the thing that I'm trying to find is side C, so I'm going to put C down first, and then in the sine law, that's going to be opposite sine C. The thing that I know is this big side here, and it's side A, because it's opposite angle A at the top here. So I'm going to put A over sine A. So let's plug in what we know here. So we're trying to find side C, so I'll just leave that as C. Angle C is one of the angles we found here, so that's 65. I'm going to say sine 65 degrees. Side A is 250 meters. We were given that. And angle A is the big angle at the top here. So that's a combination of angle 54 degrees and 25 degrees. So I'm going to call that 79 degrees. I'm just going to pause things here. You can probably hear my phone ring. Okay, sorry for the pause there. So we just discussed the fact that angle A at the top of triangle ABC is 79 degrees. So we plug that in, and now we can use those ratios to find side C. So if I do my cross multiply, so 250 times sine 65, and I'm going to end up dividing by sine 79. And when I calculate that, I'm going to get 230.8 meters for side C. So now that I know that, I can use, that's 230.8 for side C. I can now use that in the right angle triangle ABD. So in triangle ABD, Because it's a right angled triangle, I'm going to use SOHCAHTOA. To find that H value. Now, in that triangle, if I'm going to use this angle B, which is 36, if I'm going to label the two sides, this side over here that I'm trying to find is opposite, and the side that I just found, the 230.8, that is the hypotenuse in the right angle triangle, because it is across from the right angle. So if it's opposite and hypotenuse, I'm going to use the sine ratio. So I'll write it the formula, sine theta equals opposite over hypotenuse. And when I plug in the values that I know, the angle that I'm using is the 36 degrees. The opposite side to that is the height, or h, little h, and the hypotenuse is 230.8. So to find the value of h, I'm going to do 230.8 times sine 36. So I end up with h equals 135.7 meters when I calculate that. So at the beginning they wanted to know what AD was. We were using h to represent AD. So I would say, so therefore AD is equal to 130.7 meters. So that's my final answer there. Okay, and that makes sense. It's one of the shorter sides in triangle ABD. 230.8 is the hypotenuse, that's the longest side. So it makes sense then that AD, or the height of that triangle, is something shorter than that, so it's 135.7 meters. So now I'm going to move on to example 2 here. Example 2, I'm trying to find QT. So QT is this distance here. I'm going to call that x. So I'm trying to find that distance. And it's important to recognize as well that here I've got a lot of triangles. I've got this triangle at the top, which is QTS. I've got this triangle at the bottom, that is TRS. And I've got the big triangle, which is QRS as well. And so when I'm looking at side QT, it is important to recognize that QT is equal to QR, which is this big side here in the big right angle triangle QRS. And so it's equal to that side minus TR, which is this part here, which is a side TR, which is in the small right angle triangle TRS. So there are overlapping triangles as well as triangles that are beside each other here. Now, when we work with right angle triangles, things are going to be a lot easier. So, the big question is, can I find these? Because if I can find the length of QR and the length of TR, then I can find the length of QT. So let's see if we can do that. So QR is in triangle QRS. So in triangle QRS, what do I know? So angle S in a big triangle. So if I'm looking at this big triangle here, angle S is these two angles together. So angle S is equal to 33 plus 9. So it's equal to 42 degrees. So I do know that. I also know that RS, so the side at the bottom of that big triangle, is equal to 25 centimeters. So because I know those two pieces of information, I should be able to use SOHCAHTOA in that right angle triangle to find that side QR. So I'm going to label some sides here. So in that big right angle triangle QRS, if I'm working with angle S, and I'm trying to find this side QR, that side QR is opposite angle S, and the side we know at the bottom here is the adjacent side. So if I'm working with opposite and adjacent, then I'm going to be using tan. So tan theta equals opposite over adjacent. And the angle that I'm working with is this angle here, S, and that's equal to 42 degrees. The opposite side, I don't know. That's QR. And the adjacent side is 25. So to solve for QR here, I'm going to do 25 times tan 42. And when I calculate that, if I round that to one decimal place, I get 22.5 centimeters in that big triangle QRS. So I found QR. Now can I find TR? And TR is this side here. So TR is in triangle. So it's in the smaller right angle triangle. So in triangle TRS, here's what I know. So now I'm talking about this triangle, the smaller triangle, TRS. In that triangle, angle S is equal to 33 degrees. So that's this angle here. And RS is equal to 25 centimeters. So we are going to use triangle we're not going to use triangle SOH, we're going to use SOHCAHTOA. So we know an angle, we know a side, and we want to find side TR. So we're going to use SOHCAHTOA to find side TR. So let's do some labeling here so we know what we're working with. Now the nice thing here is that in the small right angled triangle, so in triangle TRS, here's the angle that we're using, angle S. So the 25 is adjacent. The side we're trying to find is TR, that's opposite. So we're going to use tan again in this situation. So tan theta is opposite over adjacent. And when we plug things in, it's going to be tan 33 equals, the opposite side is TR. We don't know that yet. We're trying to find that. And the adjacent side is 25. So you can see we're using the same formula in the smaller right angle triangle. The only thing that changes is the angle that we're using. Because in the bigger triangle, the angle is 42. In the smaller triangle, it's just the 33. So TR is equal to 25 times tan 33. So when we move the 25 to the other side, we multiply. And TR then, when we do that calculation, you should get 16.2 centimeters. So remember at the very beginning we said that QT is equal to QR minus TR. And we have just found both of those values. So QR is 22.5, TR is 16.2. So therefore, to answer this question, QT is equal to 6.3 centimeters. Okay, so I'm just going to pause there, and then I'll pick up. I know this video seems extra long today. Really, we're summarizing all the different rules we've used here, so that's why this is much longer. So example 3 here is a word problem. Ross measures the angle of elevation of an airplane to be 70 degrees. So I've got Ross on the ground here, and the angle of elevation, so the angle going up to the airplane is 70 degrees. So I filled in the 70 degrees here for that angle of elevation. 1 minute later, the angle of elevation is 30 degrees. So that means that the plane has continued to fly along for a minute longer. So now it's got an angle of elevation, and I'll call this A2. The angle of elevation at that point is 30 degrees. So that means that this angle in here is 30 degrees. All right. If the plane is known to cruise at an altitude of 10,000 meters, how far did the plane travel in that minute? So the height that the plane is cruising at is it's 10,000 meters. So this value here, the height, is 10,000 meters. That's 10,000 meters is that height there. And they want to know how far did the plane travel in this minute. So they want to know how far did the plane travel from here to here. And I'm going to extend that across to there. Okay, so we got the 10,000 meters is the altitude, so that's the height. That's why it's the distance that's going straight up here. Okay, that's going to create a right angle here, which is probably going to be helpful for us. And we want to know what distance do they travel in this minute? So from here, when Ross measured the angle of elevation where the plane was originally, that's A1. And we want to know how far did they travel in that minute from where it started over to where it was measured at the end. All right? So we've got everything labeled there. Now, much like we did in the last question, we talked about that height in the last one. Let me just take a look at that. So we talked about this distance at the top here for QT was QR subtract TR. And we're going to do much the same here because D is equal to, let's call this point here H, because that's the height, or the altitude, but we'll use H for height there. So D, this distance from here to here, is the distance from H to A2 minus H A1. So, just like I did last time, I'm going to be working in two different triangles. So, in the big triangle, so in H A2R, so that's the big triangle here, H A2R, that's the big right angle triangle. Here's what we know. We know that angle A2 is equal to 30 degrees. Well, how do we know that? Well, we know that because of our Z pattern here. So because of our Z pattern, that angle in the big right angle triangle is 30 degrees. We also know that in that big triangle, HR is equal to 10,000 meters. Okay, so we've got 10,000 meters there. And we need to label those two sides, much like we did in the last example, in relation to this angle here. So if we're talking about those two sides, the 10,000 meters is opposite, and the side that at the top here, which is HA2, that's this side here, it's equal to the adjacent side. So we're going to use tan in this case. So tan theta equals opposite over adjacent. In our case, the angle that we're using is the 30 degrees that's at the top here. The opposite side is the 10,000 meters, and the adjacent side is the side that we're trying to find, and that is the HA2. So remember when we have this situation, we're trying to find HA2, so that means we're going to swap these two things with each other to calculate HA2. So 10,000 meters divided by tan 30 degrees. And when you do that calculation, if we round it to one decimal place, we're going to get 17,300 meters. Okay? Now, just like we did last time, we're going to work in the smaller right angle triangle. So now we're working in this triangle here. So in triangle HA1R, and in this one, we know that this angle at the top here is going to be 70 degrees. And we can do that, again, using a Z pattern. So because this angle here is 70 degrees, this angle at the top, in the Z pattern, angle A1 is going to equal 70 degrees. And we also know, again, same thing, HR is equal to 10,000 meters. So in that same situation, compared to what we did before, we've got this side is opposite, the side at the top is adjacent. Okay? In both these situations, we don't know this length here. But we're trying to find this length at the top, and that's from H to A1. We need that to help find that distance that the plane has traveled in that minute at the top. So we're going to have to use that side at the top that we're trying to find. So again, we're going to use tan. So opposite over adjacent. We're going to use tan 70 this time. The opposite side is the 10,000 meters. And the adjacent is the H to A1. So we do the same thing. We swap these two guys. And when we swap those guys, we get HA1 is equal to 3,600 meters. So to figure out D, we said at the beginning, to figure out D, just got to switch to red here so you can differentiate each one. So D is equal to H2 minus H1. So the distance is going to be 17,300 meters minus 3,600 meters. So the distance is going to be 13,700 meters. Now, if we were actually getting the distance that a plane had flown, we're really not going to okay, I'm having some issues here. We'll just work our way around here, where I've got the homework listed there. But the distance that the plane has flown, we're probably not going to get a distance the plane has flown in meters. So we really need to change that to kilometers. So 13,700 meters is the same as 13.7 kilometers. So our final statement here is, our distance that the plane has traveled distance flown in 1 minute is going to be 13.7 kilometers. But what they want to know is, what is the cruising speed? Okay, so they want to know what is the cruising speed. And so we only know the distance. So the speed, if we're trying to calculate a speed, so speed is equal to distance divided by time. So if we're going to calculate the cruising speed, we are 13.7 kilometers per minute. But we really want to show that in kilometers per hour. Because really, if you're talking about a distance that you're traveling, you're not going to say how many kilometers you go per minute. It's going to be kilometers per hour, especially if you're in a plane. So we're going to take the 13.7 and multiply that by 60, because there's 60 minutes in an hour. So it's going to be 822 kilometers per hour. So our final statement then is going to be, therefore, the plane's cruising speed is going to equal 822 kilometers per hour. Okay? Sorry again for the length of our